So we started section 14.2 last time. We're taking a look at Euler circuits in this section, and we had encountered a little bit of vocabulary so far. We talked about what an Euler path and an Euler circuit are, and it really has to do with not repeating edges, right? Both of them have that feature. And then we had taken a look at a couple of examples of ones where they either did or they didn't have these features, and we had stopped with C, okay? So we're going to take a look next at Euler's theorem. Euler's theorem talks about how we create these kinds of circuits. So suppose we have a connected graph. We talked about connected before. It means that you can get from one vertex to any other vertex, okay? If the graph has an Euler circuit, that's an if. If it has one, then each vertex of the graph has an even degree. Okay, each vertex would have to have an even degree. And that should make sense. It means if you go into the point, you have to come out the point and vice versa. And then the second one says, if each vertex has an even degree, then the graph has an Euler circuit. So sometimes we would call these an if and only if statement. They work both directions. In other words, this is a really nice theorem. The second feature especially here says, can actually just count the degrees of every single corner, right? Every single vertex. And if they're all even, I know it's going to have one of these. I know it's going to have one. Now, it doesn't exactly talk about how to find one or what's most convenient for finding one, but it tells you one will exist. So I think this is the same image from the previous screen. It is. And I wanted to just show you how this works with this particular image. And so you can flip back to the page before. You don't necessarily have to redraw it, although you certainly could if you'd like. What this theorem is telling us I can do is I can just count the degree of each of the vertices. Remember, degree just means the number of edges that meet there. So what's the degree of vertex A? It's 4. How about B? 2. C? 2. D? 2. We'll just go in alphabetical order. E. I got 6, yeah. 6. F? 2. And G? 2. And they are all even. Thank you so much, Nathan. They're all even. So this one will have an Euler circuit. Okay, makes sense? So we're counting the degrees. We can say yes, it does, or no, it doesn't. So let's look at an example now. We have a different image. This one says, use Euler's theorem to decide whether the graph has an Euler circuit. And it specifically tells you, do not actually find one. Okay, it's not asking for that on this particular problem. And it says, justify your answer. So that kind of a statement inside of my math lab would mean that it would have some multiple choice ones where it would say, it works because of this, it works because of this, or it doesn't work because of this, it doesn't work because of this, right? So it's a multiple choice kind of feature. So for starters, what we're going to do is what? Find the degrees. All right, so let's just go alphabetical order again. How about A? B? 3. C? D? And E? Okay. Does it have an Euler circuit? No. In fact, one of odd degree would have been enough, and we've got a bunch of them, right? So this one does not have an Euler circuit. Sorry, there's not supposed to be a comma there. There is no Euler circuit. And the reason is because A and B and C and D all have what? Odd degree. So if you were looking at a multiple choice, some are going to say yes and some are going to say no, but the reason for them needs to identify that all 4 of those points fail, right? All 4 of them fail. All right, so that's one kind of a direction set where it just asks you to justify whether it does or it doesn't. Another kind of direction set can actually ask us to find one if it does. So this is an example of that. So this one's going to have us use Euler's theorem again to determine whether the graph has an Euler circuit. Okay, that's just like last time. Then it says, then determine whether the graph has a circuit that visits each vertex exactly once, except to return to the starting vertex. If so, write down the circuit. There may be more than one. Okay, more than one correct answer potentially. So what are we going to do to start with this? Yeah, we're going to find out if it has it by counting the degrees, right? So let's start with G. It's top left corner. What's the degree of G? H, I, J, and K? 2. Okay, does it have an Euler circuit? Yes. So the first thing to note is that yes. Is this yellow readable enough, or should I change it back to white? Are you all okay with it? Okay. Yes, there is an Euler circuit. And the reason, of course, is because all vertices have even degree. Now, secondly, we were supposed to decide if we can start somewhere and create a circuit that doesn't ever go through points more than one time, except to return to where they started with. So if you were to start, this looks kind of like a bow tie. If you started up here at G and you went around, let's just trace it around and see what happens. If I go around like this, I can't return to H yet, or I would complete my circuit and I'd be done, right? And I wouldn't have hit everything, so we don't do that. So I would need to either go up to J or over to K. It doesn't matter which one I do, and keep tracing. And what's going to happen is I'm going to run into I again, right? I'm going to hit I a second time before I can get back. So that's going to happen whether I start with G, H, J, or K, right? I've got the same image because there's a lot of symmetry in this graph. So the other option is to start sort of in the middle. But if I start in the middle and I go around one of the edges like so, again, I'm going to hit the middle and complete a circuit, a portion of it anyway, right, before I hit the other side. And as I do that, I've run into the point I multiple times. Okay, does that make sense? So as I take a look over here at my second answer to this is actually no. No matter where we start, we pass through, and it's specifically here, the point I, more than once. Right? Pass through there more than once. All right. Our next definition talks about something called a cut edge. A cut edge is an edge in a graph where if we remove the edge, we disconnect the graph. Okay? If you take the edge out, the graph becomes at least two separate pieces. Now, that doesn't happen generally with every edge of every graph. It could. Depends on the graph. So cut edges could be prolific. There could be a whole bunch of them, or they could not exist at all in a particular graph. So as you're writing that out, I'm going to draw you an image of one that has some cut edges and an example of one that doesn't have any cut edges, so you can see how these are created and what makes one edge sort of work in this definition and what makes another one not work. So we're going to do this image here. And this one's going to be a non-example, if you will, over here. All right, so in our first one, the example, there are a lot of cut edges, and actually every edge is a cut edge. So let me show you what I mean by that. So probably the easiest one to sort of visually see is BE in the middle as a starting place. So if you were to remove edge BE right here, you'd very clearly have two pieces of the graph, right? There'd be no way to get from, say, A to F, okay? So clearly that works for this cut or this edge right here. But the reality is it works for every edge. So let's actually take this edge down here. Notice if I take this edge down here, I still get two pieces. One of them is not very exciting. It's just a vertex, but it is another piece of the graph that's disconnected from the rest. And that's actually going to work for every single edge in this graph, right? Every single time I try to remove one, I'm going to create a disconnected graph. There's no way to not do that if I remove an edge. So over here, it's actually true that all edges are cut edges. So I'm showing you sort of the two extremes. This is the all edges are cut edges. My non-example actually has no edge that's a cut edge. Again, it's a very symmetric kind of graph, so it doesn't really matter which one we remove for our discussion. Let's say we remove AD. Notice if I remove AD, it's all still one piece. Now, could I remove a second piece and create it to be two distinct pieces? I can, but that's not the definition. I have to just be able to remove one of the edges. So in this example, right, this is a non-example, I should say, there are no cut edges, okay? So over here, there are no cut edges. And of course, like I said, these are the extremes. Sometimes we have cut edges, and they're not all of them, and sometimes we have cut edges, and it's everything, so we can get everything sort of in between. So we're going to take an example number 4, where we identify all of the cut edges, all of the ones where we can erase them, and we create a disconnected graph. So can somebody tell me one of the edges that you can do that with? EF, you bet. So if I were to erase this edge, I would definitely disconnect my graph. Everybody good with that? After I erase it, I'm going to put it back in because we need to have the whole graph back together to do it again, all right? So that's one of them. So EF is one. So as we list this, we're going to list it kind of like a segment notation. This is edge EF. What else? Yes, FG will do it too. So FG would be this edge. Again, it's not a very exciting two pieces, but it's still two pieces. So FG is another one. CF. So CF is this one. If I remove that one, again, not very exciting, but I do have two pieces. So CF. You're also welcome to list them in the opposite order. Like I don't have to write CF, I could write FC. It's the same thing, right? That's not a problem. Any other cut edges? No, everything that I tried to disconnect over in this sort of piece that looks like a square creates a cycle it's a cycle over there, right? I've got a circular piece or whatever, a cyclic piece, a circuit kind of piece, and it's like my non-example where it doesn't disconnect anything from the rest of it. So these are the 3 cut edges for this particular graph, okay? And we're going to be using these cut edges in our next theorem. That's why we need to have a good idea of what these are. So we're going to take a look at one that's there's me a couple here, we're going to have a fair bit of writing. This is the first one. This is called Fleury's algorithm. And what Fleury's algorithm does is it actually allows us to find an Euler circuit. We haven't done that actually yet. We've said they exist, but we haven't found them. So, at least not in general. So Fleury's algorithm says the following. Start at any vertex. Fantastic. Go along any edge to any other vertex. That's very specific, obviously, right? And you remove the edge that you go along. Okay, so you delete it out, kind of like we were doing with my cut edges as I'm erasing. You're erasing them as you go. So I kind of scribble on them, right? I have the benefit of erasing them on my screen. Yours is actually printed on your paper or on the iPad that you're using, so scribbling over them will work. So you're going to remove it. In your revised graph, you repeat step 1, but you do not cross and remove any cut edge unless you have no other choice. So we're avoiding the cut edges unless we have no other choice. And we repeat this step 2 until we have used up all of our edges and returned to the starting vertex. Now, because of the way that first statement even starts, that we can start anywhere and we can go anywhere, right? And then we can keep doing this sort of anywhereing as we go, as long as we're not going across cut edges. What that's necessarily going to mean is that there's lots of answers, okay? So again, these are going to show up multiple choice style inside of my math lab. So you're going to actually be looking at an example of one and deciding, does it actually work? Whereas in class, we're going to be finding one that works together. Okay, so that's going to feel a little bit different. But there are lots and lots of answers as you work through these, even though sometimes they'll start at a specific vertex. They don't always have to give you a starting spot, but they are going to for the ones that you're going to see. You're going to be given a starting place. Okay, so we're going to use Fleury's algorithm to find an Euler circuit for the graph, and it tells us where to begin. We're beginning and ending at A. Okay. So we're not using my notes because you guys are going to lead the discussion, okay? That doesn't always end up going well, but I think it's going to be just fine. I think we're going to be able to handle it together just okay. So as we go along these, I'm going to highlight them in yellow instead of remove them to indicate that I've traversed along them, because that will look more like what you're doing on your paper. But the idea is that we're supposed to be removing them. You just need to know we can't go back over a yellow edge. Cool? Okay, so I'm going to use yellow for that. Where would you like to go from A?
A to H.
A to H. Okay, Charity has started us out going from A to H. And here's how we note this. We're just drawing sort of dashes or an arrow between them to show where we're going next. Okay? So A to H. Now, we do not have a choice on the next one, correct? Not only that, but it actually is a cut edge at the point when I do this. My new graph, without the yellow in there, right? If you ignore the yellow piece. The new graph, when I go from H to G, does disconnect point H from the graph, but I have no choice. Do you see what I'm saying? So because I have no choice, then we will, in fact, go from H to G. But after we get to G, I've got choices. Where would you like to go next? Somebody pick one for me. J. Okay, G to J. Okay, so G to J. So I have still got it connected except for that H on the edge. But once I leave J, which I have only one choice to leave J, I actually disconnect the graph again, right? Okay, so now I'm going from J to F. I have choices again, leaving F. Where would you like to go? Okay, F goes over to G. Okay, so notice we can totally revisit points. That's not a problem. And now I only have one choice in which to leave G. I will go to A. Okay, have choices again. Where would you like to go from A? A to B. Okay, so we've got A to B. Notice there is something I can't do here. Where can I absolutely not go next? I cannot go to F. Do you see why? If I go to F, I end back up at A, and I never went over to the right-hand side of the graph. So there are some restrictions along the way, all right? So you do need to be careful about that. B does still have other places it can go. Notice you've even got this sort of wonky curved edge. That's cool. So where do you want to go next? C, okay, B to C. C has only one option. C will have to go to D. D has choices. Okay, D to B. Okay, so I gotta get the ability to draw it in curved form. All right, so D to go back to B, which is totally fine. And again, I can't go to F, right? Everybody's got that. Okay, so D to B. And then B goes to, you want to go to where? To K. All right, K has only one choice leaving it. I've got to go on to D then. D has only one choice at this point. D has to go to E. E has only one choice. It must go back to B. And then B goes to F. And F goes right back to our starting point A. Okay, does that make sense? So when you're looking at these, it will be one where you're going to actually have to look at the answers they give you and traverse and see if they work, right? So you're probably going to need some scratch paper to do that. You're probably not going to be able to eyeball this thing and make it work, especially if the graph is as complicated maybe as this one, right? Sometimes you can eyeball some things and eliminate something pretty quickly, and sometimes it's much harder to do. So be careful as you're working with them. There's no like, oh, you should start with C. C is usually the right answer. It doesn't work like that. You'll know that. So hopefully it will be an early one that you pick and not the very last one, so you don't have to do every single one of them. But this is the process. All right. So note for an Euler's path. Okay, so what we just found was an Euler circuit. Starts and ends at the same place, does not cross any edge more than once. This is an informational piece about an Euler path. Let's say you do not have all even degree. We know from our previous theorem, Euler's theorem, that then we do not have an Euler circuit. But if you do have exactly 2, not less, not more, 2 with odd degree, then there will still be an Euler path present. Not an Euler circuit, but an Euler path. However, your path must start at one of the vertices of odd degree and end at the other one. And notice, just like with an Euler circuit, there is a possibility you're given a graph that doesn't have it, right? We've actually seen one today that did not or would not have had an Euler path had we been asked. It had 4 of odd degree, right? So when it asks us in a minute here to check and see if it has an Euler path, don't just skip over that step and assume it's going to work out just fine. Especially, I guess you could if the answer choices all say that it does. But generally, that's not how they word them, right? Generally, there's a couple that say yes and a couple of them that say no. So you have to start with counting, in this case, the degrees, just like we did with the Euler circuits. We got to count them up and see if it meets these criteria. All right, shall we take a look at one? Let's do it. It's the last example in this section. Looks similar to the other graphs that we've had. It's a little different though. So let's go through and we're going to count all the degrees. Let's just go alphabetical order like we have been. What's the degree of A?
4.
Good. How about B?
3.
3. So we do have an odd degree, so it's not going to have an Euler circuit. It didn't ask us that, but just think that that's the case, right? How about C? 3. Right, so if it's got an Euler path, I have to have all evens on everything else left. Let's see. How about D?
2.
E?
6.
F?
2.
And G?
2.
All right, so does it have an Euler path?
Yes.
So yes, there's an Euler path. Whoops. Because 2 points, I'm going to put the word in parentheses only, have odd degree. And those 2 points, of course, were B and C, right? 2 vertices. All right, then. So we're going to decide we're going to create, I think it says, if the graph has such a path, say what endpoint the graph must begin and end at. So what endpoint do we have to begin at, and what endpoint do we have to end at? What are the the answers to that question. Yeah, so we have to start and end, one or the other, right, at B and C, the ones that have odd degree. It doesn't actually ask us to find one. Let's go ahead and do it just for good measure so you can see how it would work if it did ask. Okay, so make sure you only do what the questions ask you to do. But just for practice, let's do that because we haven't practiced with these a whole lot. So we have to start or end at B or C. So which one would you like to start at? B. Okay, so we're going to start at B. Where would you like to go from B? A. I heard somebody say A. So we're going to go from B to A. Then where? Lots of choices. A to D. Cool. Now we're down at D. Now we don't have a choice because D only has one exit edge. So D will go up to E. Now we've got choices again. Where would you like to go from E?
F.
F. Okay, so if we go to F, then we have to go to G and then back to E. Okay, so E to F to G and then back to E. Okay, now where from E? To A, okay. Still have choices. E to A. What's after A? Or where would you like to go after A? Oh, we only have one choice now. A has to go down to C, right? Okay, A goes down to C. All right, now where do you want to go?
B.
B. So we're going to go over here to B. Okay, C to B. And then up to E and over back to C, right? Okay, make sense? Excellent.